Welcome to our NPTEL lectures on the power quality improvement technique. We are continuing with the shunt active power filter that we are going to continue. We are discussing about the instantaneous reactive power theorem. So, this was our discussions. So, ultimately we have discussed that the theory is that the shunt active power filter should not feed any amount of reactive power, and based on that this theory is developed in alpha beta frame. So, let us see that using the condition of the compensator power given above in the previous slides, the alpha beta components of the compensator can be as follows. So, we can rewrite the value of the shunt active power filters alpha component and the beta component that required to be injected by the shunt active power filter. So, it is V alpha plus this denominator, that is the common, that is the determinant of it. So, V alpha square plus V beta square into power of this alpha beta frame of this shunt active power filter and QB. Similarly, if you can combine this equation, essentially you get this expression. So, it is 1 by V alpha square plus V beta square minus V alpha V 0 L 0, that is a load component of the this zero sequence component. Similarly, it is the V alpha V beta and I L beta and similarly I alpha, and thus this component also comes I F B. So, 1 V square plus V alpha square plus V beta square equal to V beta P alpha beta plus V alpha Q alpha beta, and 1 by V alpha square plus V beta square equal to V beta minus V 0 I L 0 plus V alpha V alpha I L beta minus V B T I alpha. Similarly, you got an expression, you see that it is almost same, there is not much difference in it, and this is denominator is same, it is V alpha square V beta square minus V 0 beta and I L. Here since it is I beta, so this will come. Similarly, this will be the cross component, it is I alpha I beta into here it is beta, so there will be alpha. Similarly, this one it is I beta square, here you will be a I alpha into I L beta. So, there is a similarity and you can check that whether you are deriving the right equation or not. Fortunately, you have a multiple choice question, but the student of this institute have been asked to derive those equations. So, ultimately you know that if you connect the 3-phase 3-wire system, so this neutral current will flow through here. So, IF will be IF 0 will be essentially IL 0, and IF alpha will have these expressions, and similarly IF beta will have just negative of it. It is beta square I alpha, it will be minus alpha beta into IL alpha, and this term will come here, but with the beta. So, once this compensator currents you can correctly compute by this block, this zero sequence component I alpha and I beta are known, they are transferred back again to the ABC frame in implement the real time, and this transformation is given in the next slide. So, this is the way we can do it. As we are discussing with the instantaneous reactive power theorem, please note that this zero sequence power supplied by this active power filter is Pf 0, and this is the load part of this zero sequence component. Similarly, the active power component in alpha beta frame should be equal to the PL minus P average and minus P average load, and that should be the power component of this load, that is here represented by PL delta. Similarly, the power of the power filter to be supplied is Pf, that equal to the 0 sequence component, that is Pf 0 plus Pf alpha beta, and that is equal to instantaneously that value will be power P delta. So, thus if you go for the matrix representation, the power component and the various component of the current can be related as follows. Here P alpha P beta, we shall use the notation P here, no Q will be used here. So, we shall see that here the alpha axis instantaneous reactive power we shall mention in a nomenclature, that is P alpha Q, that Q stands for the reactive power, but we are not, and that will be given by V alpha into I alpha Q. Let us go to this point again. P alpha and P beta can be represented as V alpha into I alpha, and the second term entity of the matrix will be V beta into I beta. Similarly, it can be expand as from the previous slide, that will be V alpha in bracket I alpha P plus I alpha Q, and in second term entity of this of the matrix will be V beta in bracket I B beta P plus I B beta Q, and that can be splitted in this forms, that is V alpha into I alpha P, and we go this column wise, then it is V beta into I beta P plus V alpha into I alpha Q, and column wise again V beta into I beta alpha. Thus, we can further expand, this term essentially will be P alpha P, that is the alpha axis real power, and P beta P beta axis real power. Similarly, this multiplication, that is cos terms V alpha into I alpha Q, that will be the P alpha Q, and that will be the reactive power in the alpha axis, and similarly it will be P beta Q. This has been named here. So, this is the alpha axis instantaneous reactive power is P alpha P, that equal to V alpha into I alpha P. Alpha axis instantaneous reactive power, here we shall name it as P alpha Q, that is V alpha into I alpha Q. Similarly, beta axis instantaneous reactive power, that is P beta P, that will be beta B into I beta P, and beta axis instantaneous reactive power in this way it will be P beta Q equal to V beta into I beta Q, and thus you can expand it. This is a real power essentially P alpha P plus P beta P, that will be V alpha into I alpha P plus V beta P into I beta P, and these terms will be coming from this determinant, solving the determinant, that is V alpha into V alpha, and that is a determinant term V alpha square plus V beta square into the total power plus. So, this term beta will be V beta into V beta, and this determinant term V alpha square plus beta square into P, and if you can combine, that essentially gives rise to the value of the P, and this determinant term will get cancelled in numerator denominator. And then you know that for the 3 phase 4 wire system, that is what we are continued discussion, this should be 0. It can be observed that the sum of the P alpha P and sum of the beta P equal to the instantaneous real power P t, and the sum of the P alpha Q and P beta Q is equal to 0. Therefore, you can add up this thing, and for the ideal compensator, this is the third harmonic component of the 0 sequence. So, P L F 0 should be equal to P 0, and similarly P alpha beta will be minus P L 0, and P alpha beta will be the Q alpha beta will be essentially the reactive power that will flow and come In practical compensators, switching harmonic losses has to be considered. These losses should not should be made from the source in order to maintain the DC-link voltage as a constant voltage. Let these losses will denote after this the P loss, and the following formulation to be used this term. So, we can see that what is P loss. So, ultimately you have the P 0 plus P loss, and P f 0 equal to P L 0, and P alpha beta equal to P L delta minus P bar, and Q alpha beta equal to minus Q L, and from this will be the active topology. Essentially this will be the flow of the 0 sequence component. If you do not have any fourth leg, if you have a fourth leg, then you can have the control of the fourth leg also by it. So, this is the way you will control. So, you have the IF ABC, and that you will be injecting from here. So, once you know once the reference currents these have been obtained, the filter current ABC system is obtained as below, as we have shown into the previous slide by the reverse transformation. So, you can have IF alpha IFB plus and IFC equal to 2 root 3 of this matrix, and now we know that IF alpha, IF beta and IFC beta, and they have to be synchronized with the voltage source. So, thus what happened, these are the alpha beta domain equations, and you have to add extra entity the P loss to meet all the losses, and you will estimate the loss, and so from there so you can have all those entities to be recalculated and refurbished. So, if you go back, so now you get this from these calculations. From these calculations, once you get this, so you go here, and by this transformation you calculate IFA, IFB and IFC. This is the way of calculating reference in case with the reactive power theory. Okay. So, this is the source, and ultimately this is a 4-way system. This is a ISB and ISC, then this is a 0 sequence component, and from there you will be injecting IFA, IFB and IFC, and this is the neutral current that will flow through the midpoint of the capacitor. So, thereafter midpoint of the capacitor, thereafter you can have a dynamic hysteresis control of the current or the PI control, and from here you will have these values IA, alpha, IA, IB and IC of the load current. Similarly, you have a source current, and you have a voltage regulator. From there you will the component of the P loss that will maintain the DC-link voltage, and this will add up. Essentially with all this calculation has been shown, you get IFA star, IB star and IFC star, and you can have a hysteresis of the PI controller to compensate this current. This is the way the instantaneous reactive power theory proposed by Akagi will work. Now, we will propose one reference generation technique, as I told you, that will be the ANN based, and see that there is another important method. Of course, another important method of the time domain is the SRM method. Here if you what happened there, you generally have this sinusoidal waveform, thereafter a system, thereafter you have a diode Bose rectifier, and what happened, you got a shunt active power filter, and in SRM method this is derived from the vector control. You will be sensing again the load current IL. So, you have this two block, we have seen the alpha beta frame. So, you have IA and IB. You have IA and IB, of course, since if it is a 3-phase 3-wire system, you know that IA plus IB plus IC equal to 0. So, you can generate the IC, or if you have a 4-wire system, then you require to sense the another current. I am considering here, since we have considered there with a 3-phase 4-wire system, I am considering a 3-phase 3-wire system. So, essentially what you will do, you will first convert to the ABC to the alpha beta frame. So, that is the buck transformation. So, you have then I alpha and I beta. Then what happened? Then you require to get the information of the theta that comes from the PLL. You will sense at least 2 or 3 voltages, that is the VA, VB and VC, and your out, this is the PLL block. PLL block essentially the phase lock loop block, and that will generate theta. I have taken a separate class on PLL. So, you are requested to refer this thing. So, theta will be there, and essentially your alpha beta component will come into the DQ component. If you take 3-phase 4-wire system, then DQ 0 will come. I am taking a 3-phase 3-wire system, then DQ component will come. And in the concept of 3-phase, and what happened, what you did, this is your phase A, and you aligned alpha with that, same way you align D with that. Initial angle between these two is 0, and you rotate with the synchronous frame, and thus you get theta. Essentially you get ID and IQ. Once you get ID and IQ, see that what happened, you know that harmonic content of IL is I assume that the 0 this DC component is not there because it comes from the quantization error mainly. So, plus IQ plus you have a harmonic. Generally the harmonic is essentially, it is 2 to infinity, if I write, it does not matter, but it will be, you know that IH essentially it is 3rd harmonic, 5th harmonic and so on. 3rd harmonic will not be there because you do not have a neutral. So, it will start from 5th, 7th and so on. So, what happened, you know, I can say then the original load current, this IP in DQ frame will come as average value ID, and IQ part in ID will be of course 0, and these harmonics will come as a delta, and I can write ID, that is corresponds to the in phase component of the voltage with the current, and similarly you can have IQ delta plus IQ, that is essentially IQ bar or the average will be this value where it is constant. So, what happened there? Thereafter what we generally do, we pass it to the high pass filter. High pass filters is realized by generally by subtracting with the low pass filters. So, essentially you get the ID delta. If you want that typical harmonic compensation, not the reactive compensation, you have the reactive compensation with the capacitor and all. So, then rating will be lower, and assume that this is the case for it, then you have the IQ delta. This ID delta and IQ delta again reconverted into, of course, first dq to the alpha beta frame, alpha beta to again ABC frame, and then it will be fed to the PWM, or and this point will go to this point. So, this is the way SRF model will work. For sake of time, I do not want to go for the detailed discussion of the SRF model, and it has a many variant, like if it is unbalanced, then what happen? Then we have to add a negative sequence of it. So, then we have to generate another sequence theta and minus theta. So, then the PLL has to perform differently. And what happens, since the D is it is something that rotating in a synchronous frame, then once you have a positive and negative sequence, positive sequence will look like stationary, but negative sequence will be rotating at a speed of the 50 hertz opposite to you. So, it will appear to the double frequency harmonic. So, those are a few challenges, and then PLL is being challenged to get that real actual value in that case. Anyway, these are the complex problem with the SRF system. Now, we shall take out one example for the with this ANN, and this is it will here the concept of this SRF will be combined. Ultimately, how accurate you generate this, and ultimately HF is splitted with this high pass filter, low pass filter, and it is been subtracted here. So, this is the constitution of the high pass filter. So, what happened here? So, how accurate you set this, because it is a DC value. You can set the cutoff frequency of 0.1 hertz, you can set the cutoff frequency of 1 hertz, you can set the cutoff frequency of the 10 hertz, and so on. So, less this cutoff frequency you set, more accurate will be the value of the delta, but there will be a delay in calculation because this low pass filter required a time for the settling, and ultimately we require to optimize. So, this training we can train this optimization and use this ANN. So, that is one of the work of the ANN I am going to present in your case. So, here for this reason initially we have talked about the direct method, and I told you that is not quite accurate, but it can use as an initial guess. So, for this reason this capacitor based algorithm here it is goes for the predicting the initial value of IP, as it has been done in case of the direct method, but direct method cannot bring the value of the TST quite satisfactorily low, because everything you put it on this filter, and there will be a tuning that will be done by the adaptive filter and to give you the accurate results. So, this is a predictive adaptive combinations of the NN that gives you the better results. I can show you this results of the simulation as well as the hardware. So, this is the little bit of to understand this phenomena, we require to understand in detail about the DC bus dynamics. So, we will be discussing now the DC bus dynamics in detail. So, this is a voltage transducers, from there you got a compensators, and thereafter you got, since we work in a digital domain, everything is in digital. So, you got a predictive value of IP. So, of course, once this sax comes from sax, you can in the capacitor voltage, because of the load change, increase in the load, then IP will estimate the value of the IP. So, and you got IC plus IST, that will be flow and maintain the current, and from there you try to guess the initial value of the IP. That is quite important, because you get, if you get a very closer value of IP, then convergence of it will be faster, of the NN will be faster. And ultimately you know that PW equal to PDC equal to CdB/dt. So, this is the value of IC, that current will sink to the capacitor into IDC, and this is the part in a alpha frame. So, it is V 3 phase, if you write in a 3 phase, that is basically I alpha and I beta, and essentially this value is going to give you the value of the PDC, that is the power consumed by the capacitor. So, from you can understand that what is mentioned as a P loss, here it has been PDC. Now, we want, this is the tuning of it, essentially we tune the weights of the NN, and this weights is going to be essentially the value of the IP and IQ. So, if you, how close you can match it. So, you have the target data and the error data. So, you have a covariance algorithm here been used, you can use any other algorithm, backpropagation algorithm or here. You have VDC and IDC, and you tune it and you get the value of the I alpha, and it has to be tuned offline, and once it is tuned offline, it will predict quite easily and satisfactorily. And now, let us come to the solution of it, and some experimental results I am showing, simulation and experimental results. So, it has been done with the MATLAB Simulink, and for sake of showing it, I put simulations and the experimental one by one. This is for the 3 phase 3 wire system, and you can, I have shown the same circuit there, where you can create the single phasing. So, this is a case of the simulation and the performance of the active power filter with predictive algorithm. So, you do not have tune it further for the adaptive algorithm, and you got this kind of waveform. It was quite sinusoidal. Thereafter, even if after it gives you this value of the compensating current, but still it cannot maintain the desired level of the THT. So, this is the same waveform with the experimental results that you will get with the ANN based predictive method, and also you can expect almost same kind of data with the active method. So, for this reason we require to have a tuning. So, this is the case of the simulations with the performance of the APF with Adeline, and what happened, you can see that it has load change has been detected. It takes this much of time to run, because it takes the data of it and it will tune online, and ultimately this matches the values of the in phase component of the power P and Q, just double checks it and gradually makes this voltage and current sinusoidal. So, this is the top waveform is the source current, middle waveform is the load current, and the bottom waveform is the compensating current, and the scale has been taken the 20 millisecond per division. Similarly, this is the corresponding current, this is a load current, and till there you can see that it is not sinusoidal. After this interval of time t2, it is sinusoidal. So, here both this algorithm are working, and so this is the performance of this adaptive and predictive controller, both are working together, and thus you can expect the first action. So, performance of the predictive algorithm controller, and thus you can see that there is a load change has occurred. So, it almost within a one cycle this has reached the steady state value. So, since what happened actually in this case, why it is better, here it works, it does not have any guess how much will be the starting point of it. So, it takes huge amount of time for the convergence, but here since you have fed with the predictive algorithm, you can guess a closer value. So, you can always converge faster, and for this reason without much loading it, because tuning is once you are tuned it will predict. So, prediction is easier. So, amount of the voltage and sags and all those criteria, amount of the load, these are the data. So, it will predict the value of the IP, and after that you require to tune it, and it will converge very fast, and you can see that within a one cycle it can simulate. But if you do the same thing that we have done in SRF technique, it is equivalent to setting the cutoff frequency of 1 hertz. So, if you set the cutoff frequency of 1 hertz, then we have seen that we require at least 4 cycle to get the desired THD, whereas you are getting this THD within 1 cycle. So, this is the advantage, and thus people now going for the, because of the higher processor rate and all those things. So, we are talking about the NN based system. So, same SRF based system is been reproduced by the NN, and you can see the benefit of it, and you can compensate quite fast and accurate. So, this is the corresponding hardware results of this is the load current, this is a source current where the load change has occurred, and from this point to this point there is a load change. So, it is compensated, you can see these two peaks are almost same, that means by the time it has been converged. So, and that is what the harmonic spectrums are. So, you can see that harmonic spectrum, that black one is your compensating current and the gray one is your uncompensated load current. So, you can see that black one is 100%, thereafter this one is 5th harmonic, this one is 7th harmonic, this one is 11th harmonic, and so on. This is the harmonic spectrum of the load current after and before compensation, source current after and before compensation. Thank you for your attention. I have covered for the reference generation technique in our discussions. In next class, I shall take on your control aspect of the shunt active power filter. That is essentially a very interesting aspect, and we are requested to revisit the control system again. Students are requested to brush up your basics in state space modeling and all those issues, so that they can find that they can understand it better. Thank you so much indeed for your attention. We shall continue to our shunt active power discussion in our next class.